An introduction to series. Let's start with the definition of a series. A series is the sum of the terms of a sequence. So let's remind ourselves that a sequence is just a list of numbers. So here we have a general sequence. We have a sub 1, a sub 2, a sub 3 are just representing numbers that are separated by commas in a list. A series is when we add those numbers together. So we have a sub 1 plus a sub 2 plus a sub 3 and so on. We can see a series expanded, but we can also write a series in shorthand using sigma notation. So this Greek letter here is sigma, and we can also call it summation notation. So instead of the expanded form here, starting at a sub 1 and adding a sub 2 all the way forever, we can write instead this big sigma. On the bottom, we can say what we're starting at, the first term, n equals 1 to infinity, because we're adding up infinitely many terms, of the general term a sub n. So down here, the vocabulary again, a sub n is the general term, n is the index of the summation. Sometimes we also see I or k. The lower limit of the summation here is 1, and the upper limit is infinity. And when that upper limit is infinity, we're adding infinitely many terms. This list goes on forever, and we call it an infinite series. So that brings us to kind of the big question in this section about adding infinitely many terms and what that means. So here's kind of that big question. Can we add infinitely many numbers together and somehow get a finite value and not just infinity since we're adding infinitely many terms? So this should give you some pause. Does that really make sense? Adding infinitely many numbers and getting a finite value? And to kind of help wrap our minds around this idea, we're going to discuss Zeno's halving paradox. And here's what it says. Before reaching a destination, you must get halfway there, then halfway again, and so on forever. So let's kind of visualize this. So here's you, and let's say you want to leave whatever room you're in right now. And so let's call the distance between you and the door a distance of 1. So this entire distance here between you and the door, we're going to call it 1 unit of measure. Well, I hope we can all agree that if you are going to reach your destination of the door, that you must get halfway there. So I'm going to do my best to kind of mark the halfway point here. So I'd have to travel halfway there. Well, if I call the entire distance 1, then this portion here, from here to here, would be 1/2. Okay, so now let's imagine we are standing right here in the middle. And in order to reach my destination, I have to go halfway again. So let me go ahead and try to mark the halfway point there in the distance that's remaining. So that means that I've traveled another distance, a total of 1/4 of the entire 1 unit. So this distance here is 1/4 of the entire distance. All right, so now we're imagining we're standing right here, and to get to my destination, I have to go another halfway. So let's cut that distance right there in half, and that next distance of the entire original length, that would be 1/8. So I can imagine chopping this into 8 equal parts. This little distance traveled is 1/8 of the way. All right, so here I am, not too far from the door now, but you'd agree that I'd have to go halfway again. And so that would bring me to about right here. And that little distance that I have now traveled in this little gap would be 1/16 of that total distance traveled there. And then I have to go halfway again. And I have to travel this little distance here. So now the paradox, or the part that can feel a little confusing, is, well, am I ever going to get there? Am I going to reach my destination if I have to keep going halfway? So if I have to keep cutting this in half, it doesn't feel like it, but at the same time, we know that we can reach our destination. We can head out of whatever room we're in right now and reach the door. So what we're saying here is that that total distance of 1 is equal to 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over, well, that next half piece is going to be 1/32, and so on. We can keep cutting this distance in half and half and in half, but we know that the total distance between us and the door was 1 unit. So look what we're saying here. We're saying that 1 is equal to the sum of this infinite list, because this list goes on forever. So can we add infinitely many numbers and get a finite value and not just get infinity? I do miss teaching this in class because I can see the wide eyes usually and the confusion. And it is a really interesting idea and an interesting concept that we're going to spend the whole chapter discussing. Now what we're going to do is be a little bit more mathematically rigorous. We're being asked, what does the following infinite series add up to? So this idea of adding 1/2 plus 1/4 plus 1/8 plus 1/16 and so on, so that general term is 1/2 to the n. So here's that expanded version, and here's the condensed summation notation. So what is this infinite series, the sum from n equals 1 to infinity, of 1/2 to the n? What does this equal? Let's try adding on terms one at a time. So we have our first term is just 1/2. And now let's go ahead and add on the second term. So we're adding a sub 1 plus a sub 2. So we have 1/2 plus 1/4. So 1/2 plus 1/4 is 3/4. And now what we're going to do is give these a different notation. So each individual term is a sub 1, a sub 2. These are now sums. Well, the first one's kind of boring because we just put the first term, but we're going to call that S sub 1. It doesn't get interesting till the second one. We're going to call that S sub 2. We're adding a sub 1 and a sub 2 together. So then S sub 3 is going to be adding the first three terms, 1/2 plus 1/4 plus 1/8. So we're adding that a sub 1, right, a sub 2, and a sub 3 together. And so that as a fraction is 7/8. And now let's try S sub 4. So we have 1/2 plus 1/4 plus 1/8 plus 1/16. And it turns out that's 15/16. Now, as fractions, we can't necessarily see just how this sequence is unfolding. So let's represent them as decimals. So we have, this is 0.5, 3/4 is 0.75, 7/8 is 0.0875. Then we're going to get 0.9375. So this is painting a clearer picture. We can go ahead and look at these sums after I add on terms one at a time. So I'm actually going to provide us with the value of S sub 5. If I add on that next term, that would be adding on 1/32, that's going to equal 0.96875. And I'm actually going to go one more out. S sub 6 is going to be 0.984375. So what we just calculated right now are called the partial sums of the series, right? Partial as in part. So each one of these was a part of the total sum. The total sum is adding up infinitely many. But can I really calculate infinitely many using this meticulous method of adding on an extra one? Well, I will technically never be finished if I continue this process. But I hope what we can recognize is that this list of outputs, these partial sums, also form a sequence. And what should we know we can do with a sequence? Well, we can determine if a sequence, if a list of numbers, converges or diverges. Here we'll recap what I just did. So this idea of partial sums, S sub 1 is really just the first term, A sub 1. S sub 2 is when I add A sub 1 plus A sub 2. S sub 3 is when I add the first three terms. So S sub n is when I add the first n terms. And we can write that using this more condensed summation notation. I can have the sum from k equals 1 to n of a sub k. And so these partial sums, s sub 1, s sub 2, s sub 3, s sub 4, they themselves form a sequence, s sub n, that will either converge or diverge. Now, I love visualizing everything on a graph. So we can visualize the partial sums from that last example on a coordinate system with n on the horizontal axis and s sub n on the vertical axis. So when we had the first sum, which is really just the first term, 1/2, so at 1, I get out 1/2. S sub 2, adding the first two terms, gave us an output of 0.75. So S sub 2 is 0.75. S sub 3, so at 3 was 0.875. S sub 4 was 0.9375, 0.96875. And then we can see these are some additional outputs when I continue to add on that next term in the sequence. So again, the input here is n, and the output here is S sub n. So this is the partial sum sequence. And so not the A values. So here, A sub 1 is 1/2, A sub 2 is 1/4, A sub 3 is 1/8, A sub 4 is 1/16. But what I am going to do is on the same set of axes here, I'm going to go ahead and sketch the list of just the individual terms to kind of compare. So when I substitute in 1, the first output in the sequence is 1/2. So it actually ends up being the same value, right? So I'm going to say now A sub n is going to be the ones in red here. And then A sub 2 is 1/4. So let's see, this is 0.2, so like 0.25. So right here, that's 1/4. And then 1/8. So that's going to be, right, even smaller down here. So now I'm just basically going to be really close to the x-axis. And then 1/16 is like even smaller, so at 4. So these are getting closer and closer to 0. So those are just the list of numbers that we're adding together. So the individual list of numbers here is getting closer to 0. But the partial sum sequence is getting closer to another number. What number is that getting closer to? Well, it looks like it's getting closer to 1. So can we tell for sure that the answer is 1? Well, we can if we find a formula. So can we find a formula for S sub n for the partial sums for this previous example here? Well, it turns out we can. S sub n is equal to 1 minus 1/2 to the n. So if we have the general term for a sequence, so this is the general term for the sequence of partial sums, we can determine whether that sequence converges by doing the limit as n approaches infinity of S sub n, or of 1 minus 1/2 to the n. Well, written like this, hopefully we can see 1/2 to the n as n approaches infinity would go to 0, and all we have left is 1, which corresponds to our graphical representation that it looks like our partial sums is getting closer and closer to 1. So we're adding on just that little tiny bit each time, and it looks like I'm going to be approaching a sum of 1. So now let's define the convergence or divergence of an infinite series. Given an infinite series, the sum from n equals sum k to infinity of a sub n, if the sequence of partial sums S sub n converges to a real number L, then the series converges to L. If the sequence of partial sums S sub n diverges, then the series diverges. So here's the main idea that the infinite series from n equals k to infinity of a sub n, that is equal to the limit as n approaches infinity of the partial sums. So if we can find a formula for the partial sums, s sub n, then we just need to take the limit as n approaches infinity of that formula and see whether we get a real number or not. That turns out isn't going to be easy depending on what the general term of the sequence is. So we're going to have a formal definition and then a lot of other techniques for determining convergence or divergence of an infinite series. So this is sort of that formal way of determining convergence or divergence of an infinite series. On this example, I want to calculate the sum of the series, the sum n equals 1 to infinity of a sub n, whose partial sums are given by s sub n equals n squared minus 1 all over 4n squared plus 1. I want to point out here that this is not a sub n. So the actual list of terms in this sequence that we're adding together, we don't know what those are. But what we are given is more powerful than that. We are given the general term for the partial sums. So here, the sum of n equals 1 to infinity of a sub n is equal to the limit as n approaches infinity of s sub n. And s sub n is given, so not a sub n, s sub n. But that's really great because now I can just use my laws of dominance to quickly recognize that if the degree of the top and bottom are both n squared, I can simply take their coefficients. So I end up with an answer to this limit being 1/4. And so that means that the original infinite series converges, and it converges to 1/4. So here, calculate the sum of the series. The sum of the series is 1/4, which means that the series converges. But this is rare. We are rarely given the formula for the partial sums. On this example, I want to compute several partial sums for the series, the sum of n equals 1 to infinity of the square root of n. So here, the square root of n is a sub n. Does the series seem to converge? All right, so let's write out several partial sums. So s sub 1 is just really a sub 1, just the first term. So substituting 1 into the square root of n, I get the square root of 1, which is 1. S sub 2 is the square root of 1 plus the square root of 2. So I'm adding the first two terms. So this is a sub 1 plus a sub 2. So this is approximately 2.414. So the square root of 2 is like 1.414 plus 1 is 2.414. S sub 3 is the square root of 1 plus the square root of 2 plus the square root of 3. And I will just let you know this is approximately 4.146. And we'll just do one more. S sub 4 is the square root of 1 plus the square root of 2 plus the square root of 3 plus the square root of 4. So we're really just adding on 2 here. So this would be about 6.146. Now, does the series seem to converge? So to determine if the series converges, we want to see if the sequence of partial sums is converging. So we are looking at the outputs here. This is forming its own sequence. So we want to know, does the limit as n approaches infinity of s sub n appear to converge? Well, look at these outputs. They're just getting bigger and bigger and bigger. We're adding on a bigger number every time. So this looks like it goes to infinity, right? And that's not a real number. So that means that the limit of the partial sums diverges. So that means that the series seems to diverge. So does the series seem to converge? No, it appears to diverge. And so if we look, those outputs of the partial sums are just continuing to increase. Before moving on, let's just talk about a couple of properties of summation and then some things that are not true about summation. So if the sum of a sub n and b sub n converge, now we know what that means. If each of these sums converge, then the sum of a sub n plus or minus b sub n is equal to the sum of a sub n plus or minus the sum of b sub n. So basically, I can do each one separately if the general terms are added or subtracted. And if I have the sum of k times a sub n, where k is a constant, then I can go ahead and factor that k, that constant multiple, out of the summation. But here is what is not true. If I have the sum of a sub n times b sub n, unfortunately that is not the product of those two individual summations. And the same thing if I have the sum of a quotient of a sub n over b sub n, I cannot simply take the sum of the a sub n over the sum of the b sub n. So let's recap a big main idea. To determine the convergence or divergence of an infinite series, the sum of n equals 1 to infinity of a sub n, we can evaluate the limit as n approaches infinity of s sub n. So that's the general term for the sequence of partial sums. So the sum of n equals 1 to infinity of a sub n is equal to the limit as n approaches infinity of the partial sums s sub n. But what if we can't find a formula for the partial sums sequence? How are we going to determine whether an infinite series converges or diverges? So let's say we have this infinite series and we want to know if it converges or diverges, but we don't have a formula for the sequence of partial sums. How are we going to determine whether that infinite series converges or diverges? Well, here's an important theorem that can help us understand at least what it takes for an infinite series to converge. If the sum of n equals 1 to infinity of a sub n converges, then what has to be true is the limit as n approaches infinity of a sub n, the general term here, has to equal 0. So let's repeat that again. If the infinite series converges, then the limit as n approaches infinity of the general term must equal 0. So informally, this means for an infinite series to converge, for an infinite list of numbers to add to a finite number, those individual terms must be heading towards 0. And that should make sense. Those individual numbers that are at the tail end of that list of numbers we're adding on, they have to be getting closer to 0. Because if we're adding on bigger numbers and bigger numbers and bigger numbers, then that list of numbers is going to add to infinity. So the only way that a series can converge is if the limit of the individual terms that we're adding up are getting closer to 0. So let's make sure we really understand this idea. Recall that the sum of n equals 1 to infinity of 1 over 2 to the n converges. We said that this converges to 1. And notice that necessarily, because it converges to 1, the limit as n approaches infinity of the individual terms, so 1 over 2 to the n, a sub n, is equal to 0. So the denominator is getting bigger while the top is staying fixed. So the individual numbers are going to 0. And I did actually mention that when we visualize things. So we had the visualization of the partial sums, that is these blue dots up here that we're approaching 1. So we know that the infinite series added up to 1 as we analyze the limit as n approaches infinity of the partial sums. But then on the same grid, I sketched a sub n, just those individual terms, a sub 1, a sub 2, a sub 3. So notice that those values are getting closer to 0. So the only way we can have a convergent infinite series is if the individual numbers that we're adding up together are getting closer and closer to 0. All right, so before moving on, unfortunately, the idea of the individual terms going to 0 is not enough to say that the series converges. So if the limit as n approaches infinity of a sub n does happen to equal 0, so if the individual numbers are getting closer to 0, that does not mean that the series converges. So it's really important to understand that difference. If a series converges, then for sure the limit of those individual terms is going to 0. But just because the individual terms are going to 0, that's not enough to guarantee that when you add them all together, that it's a finite number. So it doesn't mean that the series converges. So the direct statement that a convergent series implies that the limit of the general term equals 0 does not guarantee its converse, that if the limit of the individual terms is going to 0, I don't know whether the sum of all those terms is a finite number and therefore converges. I understand that it can be kind of confusing, but the better you can wrap your mind around this big picture concept now, the more you're going to save yourself from making one of the most common mistakes in this unit going forward. So really try to wrap your head around the idea that was explained in this page.